Angles of elevation and depression. By the end of this presentation, you should be able to solve problems involving angles of elevation and angles of depression. Angles of elevation and depression are just ways to describe where an angle exists within a problem, basically. So, the angle of elevation, think of it as an elevator, so it's going up. If you're on ground level, i.e. horizontal, you're looking at the angle that's up from that. So theta here is an angle of elevation. If you're looking at angles of depression, you're looking at going down. So you're feeling a little bit depressed, you're feeling a little bit down, you're looking down. So from the horizontal down is an angle of depression. So angle of elevation, angle of depression. The good thing about this is that there's a direct relationship between the angle of depression and the angle of elevation. In fact, they're equal to each other. So if you've got two parallel lines, and they do have to be parallel to each other, then a line bisecting those or cutting through those, i.e. this line here, will always present a case where these opposite angles, this theta here and this theta here, are actually exactly the same. So my angle of depression in this case is equal to my angle of elevation. This can be quite handy if you're given certain information and you need to create some form of a right angled triangle. So we'll have a look at a case like that a little bit later. All right. So, example 1, it's a park ranger that measured the top of a plume of volcanic ash to be at an angle of elevation of 29 degrees. From her map, she noted that the volcano was 8 kilometers away. She calculated the height of the plume to be 4.4 kilometers. She wants us to show, or we need to show, how she might have done this, and we need to give the answer correct to one decimal place. This is an interesting question. It's a show that question, which is actually a style within itself. So in a show that question, you're given the answer in the question. So the answer to this, correct to one decimal place, is 4.4 kilometers. So we have an answer already, yet we're still going to do this. And the way we're going to do this is we're going to use the 8 kilometers and we're going to use the 29 degrees. And those two values we're going to use to calculate 4.4. So that's what we're showing, how she calculated the 4.4. So like normal, we set up a diagram. So we're going to use this as our diagram. We've got 29 degrees, we've got 8 kilometers, and that's what we're trying to find, which is the height of the plume, which is 4.4, but I'm only putting it in as X because we can't use the answer in our calculations. Show that question, cannot use the answer in the calculations. So, labeling my diagram with my O and my A, so X is O, 8 is A, and we recognize that this is a situation for tangent. So tan theta is equal to O over A, and I can then substitute in values and then rearrange to get 8 times tan of 29, which I can use my calculator for. Make sure your calculator's in degrees, and I get out 4.436, etc., etc. We wanted one decimal place, so this is 4.4, and it's in kilometers. So we had the answer of 4.4. This here is us showing that the answer is 4.4. So we've answered the question by showing how the ranger got 4.4 kilometers. All right, example 2. From the top of a cliff 61 meters above sea level, Chen saw a capsized yacht. He estimated the angle of depression to be about 10 degrees, and we wanted to know how far was the yacht from the base of the cliff to the nearest meter. Now, in order to do this, drawing a diagram again, but the interesting thing is the angle of depression. So angle of depression is looking down from a horizontal. So Chen is up the top of this cliff, so he's at the cliff top, and when he looks down to the yacht, it's at an angle of depression of 10. So in fact, our 10 is actually going to be up in here. So I would expect us to put that there in a second. I'm going to put a dotted line. The dotted line is always handy. I can use that as, I suppose, a fake horizontal line. So the horizontal line, the real one, is down on the sea level. This is just for our calculations. So it's just a dotted line. And then that's 10 degrees. And I also know that the cliff is 61 meters. Now, using the property that angles of elevation is equal to angle of depression, I can say that this depression is equal to this elevation. So 10 degrees is equal to 10 degrees. So I'm going to put my angle in here as 10 degrees. I can then go label like normal and then solve this using tan, substituting my values, and then I'll use the calculator. So x is going to be equal to 61 divided by tan 10, which is 345.948-ish, 946, sorry. No, 948. So this rounds up to 346 meters. This is one method. So I've used this triangle in here to do this calculation. What you could do is actually create a rectangle though. So use this fake horizontal line and then go down here. And this length down here is the same as 61. So you could have a different triangle that exists here. You'd get the same result and your calculations would look the same as well. It's just another way to think about it. Example 3 is a cable question. So a cable 100 meters long makes an angle of elevation 41 degrees with the top of a tower. So that's actually already in our diagram. So 41 degrees is here. All right. Part A is asking us to find the height of the tower to the nearest meter. So height of the tower to the nearest meter, we label our diagram with O and H and then use sign to do our calculations. Into our calculator, 100 times sine 41. Which gives us a result of 55.6, which to the nearest meter is 56. Part B is find the angle of elevation, alpha to the nearest degree that a cable 200 meters long would make with the top of the tower. So alpha is this angle of elevation in here, where our hypotenuse is now 200, and our height, the height of the tower, is what we've just calculated. Now there's some flashing light issues with this. So when I go through and do it, my normal calculations occur. So find the ratio, awesome, substitute in what I know, great. Now when I substitute in, note what I'm substituting in here. My opposite side length, my height, although I've calculated that to 56 meters, that's been rounded to the nearest meter. So that's not accurate. 100 times sine 41 is accurate. So note what you're actually putting in here is the exact and not a rounded value. If you put in a rounded value, you will get rounding error for this question. Divide it by the 200 like normal, and then this is what I put into my calculator. Now, when I put this into my calculator, I can't be bothered retyping that top line. So instead of retyping it, I'm actually just I'm going to retype it. What you can do, though, is go up and highlight this. So if you press up, it will highlight this. Press enter, and it will copy it straight down in here. So it will do that for you. Divide that by 200, and decimal value is 19.149. I'm after this to the nearest degree, so we're looking at 19 degrees.